In this lesson, you'll learn to graph and analyze square root functions and graph square root inequalities. How are square root functions used in bridge design? The Sunshine Skyway Bridge across Tampa Bay, Florida, is supported by 21 steel cables, each 9 inches in diameter. The amount of weight that a steel cable can support is given by W equals 8d squared, where d is the diameter of the cable in inches and W is the weight in tons. If you need to know what diameter of a steel cable should have to support given a weight, you can use the equation d equals the square root of W divided by 8. If a function contains a square root of a variable, it is called a square root function. The inverse of a quadratic function is a square root function only if the negative range is restricted to non-negative numbers. So you can see here that the green graph is a relation that is not a function because it does not pass the vertical line test. But when they restrict the range to exclude the negatives, it works. So when graphing a square root function, determine when the radicand would be negative and exclude those values from the domain. For example, one they asked us to graph the function and state the domain range x and y intercepts. To find the x-intercept, I'm going to solve it so that x equals 0. So add 1 to both sides and multiply it by the reciprocal. So I get x equals 2/3, which was the first value in their table because we cannot have square roots of negatives, so that is the smallest that x can ever be to give us a real solution. Since we can't have square roots of negatives, our domain has to be x greater than or equal to 2/3. We can have the square root of 0, that's okay, it's 0. Range, I can see either from the table of values or from the graph, is going to be y is greater than or equal to 0, because my smallest y value, either in the table or on the graph, is at 0, and it goes up from there. And the x-intercept we found was at 2/3, and because our domain is greater than or equal to 2/3, there will not be a y-intercept on this graph. And again, you can be convinced when you look at the graph itself, because you can see it's going to keep going to the right. We're never going to get over to x is 0. When an object is spinning in a circular path of radius 2 meters with velocity v in meters per second, the centripetal acceleration a in meters per second squared is directed toward the center of the circle. The velocity v and the acceleration a of the object are related by the function v equals the square root of 2a. Graph the function, state the domain and range. Now we can see that to get our y-intercept and x-intercept, they're both going to be 0. And if we substitute values in for a or x in your calculator, they're going to be positive, and so is the velocity. So we can plot points on the graph, and we've got 0, 0, 1, 1.41, 2, 2, that's a nice one. 3 is 2.45, 4, 2.83, 5, 3.16. So it doesn't go up very quickly, but it's still going up. So our domain, we can't have any square roots of negatives, so domain a is greater or equal to 0, and the range is also going to be greater than or equal to 0. Then they ask what would be the centripetal acceleration of an object spinning along a circular path with a velocity of 4 meters per second. So to solve, we can square both sides. So I have 16 equals 2a divided by 2, and I have a equals 8. And if you just hit the down arrow on your calculator a few times, you could have found it in your table as well. So it would be 8 meters per second squared with our label. A square root inequality is an inequality involving square roots. You can use what you know about the square root functions to graph square root inequalities. Graph y is greater than the square root of 3x plus 5. We can't have the square root of negatives, so a good place to start is to find out what is the absolute smallest value that we can have for x. and I get -5/3. So we're going to start with that smallest value, use the table feature, get some nice points. So our smallest value is at -5/3, 0. We got -1 is at 1.4, 0, 2.2, 1, 2.8, 2, 3.3, and you could just keep going using your table feature. And they connected this with a dashed line because it's greater than, the boundary is not included. And then pay attention to your shading. We have a restricted domain. The smallest it can be is -5/3. So when you shade above, because it's greater than, you want to start at that -5/3 part and just shade above the region that works. You can't shade over here because it's not defined. And once again, to graph, we want to start off by finding what is the smallest value we can have in our table for x. So I set it equal to 0 and we're solving. Oh, that doesn't come out very even. So the smallest value I can have is -8/3. So I know when I put in -8/3, I'm going to get out 0. -1 gave me 1.5. 0 is, of course, 2. Square root of 4 is 2, yeah. 1 is 2.3. And we can keep going forever if we want, but that's enough to get us start, plotting some points, and draw a nice smooth line. And this time, it's going to be a solid line because the boundary is included. Once again, I'm going to warn you, pay attention to your shading. The smallest value x can be is -8/3. So don't go shading over here where x is undefined. We're going to shade straight down from the -8/3 and everything else that's under our square root graph. You can graph square root inequalities in a similar manner as graphing square root equations. So watch out for your minimum value because you can't have square roots of negatives, so find that first, and then use that given domain to make a table of values and plot your points.